Hello physical science students, in this short video I will show you how we can use the PHET simulation on gas properties to simulate atmospheric pressures, specifically the differences with height. You probably know that high up in the mountains pressure is thinner, air is not as dense, not pressure is thinner, the air is thinner because it is not as dense as down where people normally live, and so the atmospheric pressure high up in the mountains is smaller. This has interesting consequences for people who want to go there, or if you want to, for example, cook high up in the mountains. It's going to take you longer to make potatoes, for example, to cook potatoes than where we normally cook them because of the small atmospheric pressure. The atmospheric pressure is actually connected to the boiling temperature of water, and so water will not boil at 100 degrees Celsius, but will boil at a lower temperature, maybe 95 degrees Celsius, high up in the mountains, and so it's going to take longer to cook your potatoes. These mountain climbers, they experience these lower pressures, and if you're not used to, you need to wear an oxygen mask basically, otherwise you wouldn't get enough oxygen into your body. I used to live in places where I was high up above sea level, and when I got there it took me a few weeks to get used to those conditions, and for a while it felt like I just didn't get that. I was always trying to catch my breath. I didn't feel like I had enough air in my lungs. Also, people who work in extreme conditions down in the sea, they experience the opposite of this. The pressure there is so high that without specialized equipment it would kill them, it would crush them. It is interesting to know that on the surface of Venus, so not in the sea but on the surface of the planet, the pressure is about as big. The atmospheric pressure from the gas around is so large as about 1 kilometer deep on Earth, deep in the sea. So if you landed in a spaceship on the surface of Venus and you would walk out of the spaceship, the atmospheric pressure would kill you. There's so much pressure. The atmosphere of Venus is so thick. So let's go back to our PHET simulation and let's put, let's say, 100 molecules of air. Now air is a mixture that's composed about 70% of nitrogen molecules, 20% oxygen, and the rest is water, carbon dioxide, and depending on where you live, other molecules. What we can do in this simulation is that we can turn on gravity in here, and so we can show how gravity affects the distribution of these molecules. And you might need to give it more time, or I guess let's go to lots of gravity so the effect is more visible, and you can start seeing that there are really less molecules up here, and the majority of the molecules is sort of down here on the bottom of this container. So again, the molecules are not distributed equally throughout this volume, and this is the same as on Earth. Because of the gravity of our planet, the air down at the bottom of this container, which is where we live on the ground, the air is more dense than high up in the higher portions of the atmosphere. We can also show this by numbers, because we can choose one of these measuring tools. Here is a layer tool, and this layer tool tells us what the atmospheric pressure is at this particular altitude in this container. And the numbers are not as important right now as just to see that there is a difference. So when I go up here into the higher part of the container, you can see that the atmospheric pressure here is about 0.27 atmosphere right now at this moment, and it fluctuates. It goes up and down because the molecules are bumping into the container at that height. That there's not a constant number of molecules bumping every second, and so the pressure fluctuates. Yeah, but you can see that it's, the highest that I've seen it here was 0.27 atmosphere. 1 atmosphere is the standard atmospheric pressure. It's equal to about 100,000 pascals, or 1 kilopascal. Sorry, 100 kilopascals. So if I use this layer tool and I move it down here, you can see that the atmospheric, or the pressure of the gas, from the gas, the pressure in the container down here on the bottom is just much larger. It was 0.27, now it's 1.4. So 1 full atmosphere larger than what it was before, or 1 point something larger. Anyway, this is just to show you really what our atmosphere looks like. It's a bunch of gas molecules going around. Now there are many more of these gas molecules, and here in the simulation it looks like there are these big gaps between the molecules. But you also look at these, the scale in here. It's a very small scale in nanometers, so basically billionths of a meter. So maybe it's showing, actually, for this scale, it's showing how the atmosphere really is. There are many molecules of air in any small amount of volume of space where you and I live, but they are individual molecules, and they're in constant motion. They're bumping into each other, and they're not distributed equally when it comes to altitude. Down where we live, the air is more dense, and high up in the atmosphere, air is less dense.